Today we are going to talk about the stars and bars problem. To do that, we want to solve the following exercise. What we want to do is to find all the possible solutions for this equation here on the natural numbers. We have to notice that n is a natural number as well. But to understand what are they asking for, I would like to provide you with an exercise. Look, what happens if we have the following equation? We have x plus y equals 2. How many solutions can we have for this equation? We can compute that. We can have the following one. 2 plus 0 equals 2. We can also have 0 plus 2 equals 2. And the last one is going to be 1 plus 1 equals 2. It means that this is all the possible solutions that we have for our equation. And we want to compute that for this general case. Now, why this is called the bars and star problem? That's why we can represent this using bars and stars in the following way. We can map this into two stars and one bar. So we can notice that the stars represent the value of this number, and the bars represent a space between these two variables, x and y. Now, how can we represent these solutions using binary words? It is really easy. We are going to say that every star is going to be a 1. It means that we have 1, 1, and a bar is going to be a 0. Now we can see that this solution can be represented using bars and stars or using binary words that I prefer. In this case, it's going to look like this. For this solution, we are going to have a bar and two stars. And in binary word, it's going to be 0, 1, and 1. For the last one, we will have a start, a bar, and another star. We have a start, bar, and start. Using a binary word, it's going to be 1, 0, 1. Why this is important and why I am trying to explain this to you? It's because we are going to solve this using combinatorics. And what we want to do is to compute the spots that we can take for the bars and the stars, or for the ones and the zeros. So we are going to compute in how many ways we can choose the following spots for ones or the following spots for 0. I hope that the previous example was clear, because now we are going to use that in order to solve this exercise. Now let's start. What I want to do first is to compute the set of all these possible solutions. How is going to look this set? This set is going to be, let's name this set S, and this set is going to be S of x1, x2, and so on till xm, that belongs to this natural to the power of m, such that the sum of x1 plus so on xm is equal to n. We are looking for this set, and we are looking for the number of elements of this set. It means that we are looking for this, the absolute value of this set. Now, as I promised, we want to use binary words in order to solve this exercise. To do that, we are going to consider the following injection. So let's consider the following injection. The injection phi from naturals to the power of m to these binary words. And what is this? What we want to do is to take these values. For example, let's take one of the solutions that may be C1 and so on, Cm, and we are going to map this to the following binary word. For example, 1, 1, 1, 0, so on, 0, 1, 1, 1. And what is going to be this one in here? These ones are going to be the number Z1. This is going to be Z1, and this is going to be Zm. As you remember, the numbers ones that we have in here is the number of set that we have. For example, if Z1 is equal to 2, it means that we are going to have two ones. In this case, for this example, it means that Z1 is going to be equal to 1, 2, 3, 4. And in this case, Zm is going to be equal to 3. We are using this injection. And why we are using this injection? Because now the problem that we want to solve is how many ways can I choose a spot for these ones, or in how many ways can I choose a spot for the number of for these zeros. And how is that? This is really simple because we are going to use what we already know for combinatorics. But before that, let me see what is this phi in here. We are looking for this phi, but we are looking for the image. Yeah. So let me write the image of phi in here. This is going to be equal to, let's say, alpha 1, alpha 2, and so on till alpha t, such that alpha eta is going to be 0 or 1. This is below. And t is going to be the whole amount of zeros and 1 that we have. And how many we have? We are going to have n minus 1 zeros, n minus 1, plus n ones, plus n. So this is for 0, and this is for the number of ones that we have. Why n minus 1? If you remember the number of bars, we can also see the number of bars as the number of plus that we have in here. That's why we have n minus 1 zeros and n ones. This is going to be the image. This is going to be the image. And now the problem that we have to solve is to find how many binary words we can have of length t, n minus 1 plus n, such that we are choosing n ones. It means that we are choosing the numbers, it means that we are choosing the spots for these ones or for these zeros. And we know that this is just going to be n minus 1 plus n, choose n when we are looking for the spots for 1, and this is going to be equal to n minus 1 plus n, choose n minus 1. when we are choosing the spots for 0. And this is the solution. This is the numbers of way that we can choose such a binary words. And this is going to be the number of solutions to our equation. So this image is equivalent to this S. And now let's see what happens when we have the previous example. X plus y equals 2. In this case, m is going to be equal to 1, 2. N is going to be equal to 2. And using this, let's try. We know this. Now let's see, using this, how many solutions we have. We have n minus 1. It means we have 1 plus n. This is going to be 2. And choose 2. This is just going to be 3. Choose 2. And this is just 3 factorial over 2 factorial times 1 factorial. And this is just 3. And as you remember, 3 was the number of solutions that we have for these equations. We have 0 plus 2, 2 plus 0, and 1 plus 1. And if you can see here, we have 3 of them. So this is the solution. This is the way to calculate how many distinct solutions we have for this equation on the natural numbers.